Okay, good morning, everybody. I hope everyone's having a wonderful day. So, before I get started, I just want to remind you that Assignment 2's deadline is coming up next week. So, if you haven't gotten started on that, I encourage you to get started. So, before we get started, are there any questions or concerns out there before we get back to talking about dictionaries? If you're ready for some more dictionary fun, give me 2 thumbs up. I'm getting some thumbs. It's too bad I only have one on my hand. If I had like 20, then I could try to. Actually, I would need at least 5 to match everybody. Oh, no, it's going down. That's okay though. Anyways, if that's the case, why don't we get started here? So last day I introduced you to the idea of a dictionary. So it's an abstract data type that supported a set of operations that you would associate with searching, insertion, and removal. And in particular, it stores records. And these records are pairs, each with a key and a value or data. You can think of this value or data as a pointer to some object, or it could just simply be that this entire record is an object that is being pointed to in the data structure. So another thing I wanted to mention, last day I mentioned that this is also called a map. This is in fact the case also in the standard library. So if you go digging around, you're like, hey, look, I want to see how I could play around with a dictionary. It's called a map. So there's a bunch of different kinds of maps, and we'll talk about 2 kinds in this course. So we'll talk about the most general kind, where we have the setup I introduced you last time, but also we'll talk about later on the idea of what we call an ordered dictionary or an ordered map, which I'll make a remark about in a little bit. So you might ask, Dan, why is it called a map? So it comes back to the idea of a function. So I'm just going to draw you a fun picture. So suppose I have a function called f. Now I know you're like, Dan, we already talked about functions a while ago. Like, why are we talking about that now? So remember, a function takes an input and it produces output we call f of x. So you think of it like a machine. But another way you could think of this is that this is the input, and the function will tell me what the output is. So each of these you could think of as a pair. The input and the output. So whatever would be the output of the function is, say, the second element in the pair. So this is rather intuitive to the idea of a dictionary, right? So you can think of this like almost of sorts like a lookup table, which is often what you might think of a function like. But you may have heard me use this word called mapping. I map from the input to the output. This is the same thing we're talking about here. So for example, in our case, it's a function that takes in as input a key, and it gives me the value. So if you're wondering why some call it a map, it's because it's using the same concept of a function. So if you ever learn the formal definition of a function, like there's a very specific formal one that's based on something called set theory. It defines it often as the function where you have things like this set up like they're pairs. So that's actually where this idea comes from, at least from the mayonnaise and mustard kind of stuff. So I thought I would mention that. So I wanted to come back to our discussion from last day about how we can implement a dictionary using some of the structures that we're familiar with. So we started off with a linked list, and I just presumed that it was going to be that it maintains it unsorted. So it doesn't really matter if I sort it or unsort it. You're going to run into a very similar circumstance. So when I try to access the records, I traverse through the linked list and I can find it, right? In the worst case, it just simply doesn't exist, or it's right at the end of the linked list, meaning it's going to take linear time. To put it in for an insertion, remember, there's an additional constraint on the dictionaries. We require that these keys are unique, so you cannot put in a record that has a duplicate key. Otherwise, we have to throw an error, but we have to be able to detect this if that happens. So in the worst case, you're going to have to go through all the elements, and this happens regardless. I have to traverse through the linked list to know I can perform the insertion, right? So I would traverse through the linked list. I could even insert it right at the end because I'll already be right there if I wanted to. Removal, again, it may be the case that it's actually not even in the dictionary, right? So I would have to go through the entire thing. Notice that if I maintain that the linked lists maintain these records in sorted order by key, if I could even assort them, so I'm presuming at this stage that the keys don't necessarily have to be able to be sorted, but if they could be, you'll notice that these time complexities aren't going to be any different. Actually consider the instance where I give you a collection of records where the largest key always gets inserted last. So what happens is, imagine you have a linked list where every single time I do an insertion, it's always going to be the next largest key. And imagine I attempt to try to find a key that's slightly larger than that. You'll find you have to go through the entire thing regardless. And these two don't change regardless, because you can have it where you have to find it regardless. You have to know if there's a duplicate or not. In this case, you could just simply have it by the same setup that I talked about here in a moment. So sorting it doesn't actually add anything. So if you just need to use a linked list to implement a dictionary, just having it unsorted doesn't really give you anything more if you just were to try to sort it. So maintaining an unsorted linked list or an unsorted list, you'll get these, and that's not very surprising. However, if I can sort the keys from smallest to largest, for example, and imagine I put them in a sorted array. So imagine I have a setup like a sorted array, and now I consider these three operations. So imagine I have a sorted array. So I have an array. And say I have some records in here. I don't know, I'll call them A, B, C, D, E, like this. And suppose each one of those is a pair with a key. And I would like to find, say, a given key. If it's sorted, what can I do with an array where the keys are what we'd call comparable, for example? What can I do? Can I improve on this linear time? Right here for get? Can I improve upon that? Think about the things that you know you could do with a sorted array. What can I do? Can I improve that linear time operation there? Yes, you can use binary search, exactly. So you know I can improve that get operation. I can use binary search here, right? So that's a nice improvement, assuming I can maintain a sorted array. So that's great. Inserting and removing. Now, this is where it gets a little bit trickier. Notice that if I attempt to do an insertion or a removal, I need to maintain the array in a way such that all of the elements are contiguous, meaning they're right beside each other. So for example, if I attempted to remove, say, C right here, and I tried to do binary search, and I make a guess, and it's like right here. There's no record right there. So I would have no idea if I've got a match or not. I would have to specialize things further. But there's another issue. There might be gaps that exist in here. And I would not like that to happen. So whenever I do an insertion into the array, because I want to maintain a sorted array, I would do something akin to something like the linked list, where I find the appropriate spot, I put it in, and then I shuffle over the elements, like one pass of insertion sort would. So if I do that, you'll notice that if I need to do an insertion, it may be the case that I have run into one of two circumstances. I insert it into the appropriate spot, there's enough room for it in the array, and I just shuffle over the appropriate elements. If the array becomes full, what do I have to do? What choice? I don't have any other choice but to resize, exactly. So that's what's really going to bite the bullet on us improving the time complexity here, is I have to resize the array if it becomes full. For removal, you might say, Dan, I could just use binary search to find it, right? And then I need to remove it. But here's the problem. When I do that, we have the situation where I'm going to have gaps in my array like this, where I just don't know what to do anymore. So I'm going to have to shuffle over the elements to fill in that occupied spot. So how many shuffles can at most happen in terms of big O? How many swaps, to be a bit more precise. Shuffling is just the same idea, just swapping. I'm just moving over adjacent elements. Yeah, it's big O of n. I'm going to have, in the worst scenario, I'm going to have it where I remove the first element, then all of these are going to have to move over. Yeah, so notice that in this case, we're going to end up with big O of n. So we did make some improvements, but that was just because we're able to sort the keys. It's like the keys can be sorted or placed in a way such that I can order them from smallest to largest or largest to smallest. But we can make some improvements here. Here's something that I hope will get you a little excited. So remember, logarithmic time is exponentially faster than linear time, just as n is exponentially faster than 2 to the power of n in terms of big O. So this is much faster than n because logarithmic functions grow much slower than linear functions do. So something I want you to keep in the back of your mind as a big picture view of this course. By the end of this course, if we can sort the keys like this, I'll be able to show you that you can actually improve both of these. So everything is big O of log n. That should get you kind of excited. So that'll be kind of one of our end goals in this course, is I'm going to start showing you ways we can try to achieve this. At this stage, we're running into something that's akin to something like a trade-off, where for some of our data structures, if you implement it one way, you end up having a very fast operation for one implementation. Then there's some slow ones for some other operations. But I'm going to try to meet kind of a sweet middle for some cases so that we can really see that we can try matching the best known one for one of our operations rather than having this weird trade-off thing happen. So one thing I wanted to point out as a phenomenon to prime you for what we're going to talk about next is I want to come back to the idea of a linked list. So remember, in the linked list, one issue we have when we're trying to implement the dictionary is we may have to traverse through all of these nodes, right? We may have to go actually scan through all of them if I'm trying to do my get operation, for example. What I would like to do, me being big-brained here, I'm going to use my galaxy brain here to think of something else to try. So imagine I had some way to make this linked list shorter. If I can somehow make this list shorter by making more linked lists, so for example, instead of having one linked list that had 3 elements in it, I would have 3 linked lists each with 1 element in it, and I knew exactly which one I could access to get my record. Would that reduce the time complexity, or at least my expectation of it? So if I knew exactly which linked list to look at, and it's a shorter linked list. So the idea would be, I'm going to try to make it so that we can have multiple entries, but I want to have it, the idea that we're going to have, at least this is where we're going to be going with this, at least I hope you'll get kind of excited about this, is that I'm going to get it so that I'm going to try to have it so I can have multiple spots. I'm going to call them slots for the sake of discussion, where I'm going to imagine I put each one of my elements in there. But the thing is, I would like to have some mechanism so I can know which collection do I access to find it. If I can make these linked lists really short, or at least the expectation that I don't have to go through the entire list is less, sure, in the worst case, you'll still have to go through that list, but it will be shorter. So if I can make these lists shorter, I can reduce the complexity. So that's going to be one big intuition I'm going to give you for how we can maybe try to improve the complexity for our operations for the dictionary. And that's going to bring us to our next topic, hashing. So what I'm going to do to set this up, I'm going to use some additional space. And I'm going to use this additional space to store the records. Now, depending on how we do this, we're going to see there's a few different ways we can try doing this. The idea is going to be that I'm going to build what I'm going to imagine I have like an array. I'm going to think of it more like a table, where I'm going to imagine, instead of thinking of it like a contiguous thing starting at 0 all the way across, I'll imagine it like it's a table that I read from top to bottom. So if you ever heard of the idea of a lookup table, we're going to use an idea that's like this. So what we're going to do is we're going to try to improve the time complexity of the main dictionary operations using an idea like this, where I would like to know if I can reduce the amount of, or the complexity of performing one of my operations by having to simply examine less elements. But if I can make it so that I have some mechanism of uniformly, roughly, or at least practically speaking, if I can uniformly spread my records across all of my collections, and I make sure that these are really, really short, I can reduce the time complexity, at least what I would expect on average. So we're going to use more space and this idea of hashing to construct things we call hash tables under very specific circumstances. So this is a mixture of something where I'm going to give you some assumptions to allow this to work, and I must stress that I don't have to make any assumptions about the keys being sorted. So this is a little bit more general. So this is best compared against if I gave you an unsorted array and an unsorted or sorted linked list. So what I'm going to do is I'm going to imagine I have an array, which I'm going to refer to as a table or hash table. And I'm going to always presume, for our sake of our discussion, that it's going to have as its size or length capital M, which is always, for our discussions, unless I otherwise state, it's always going to be at most the number of elements I'm actually going to put into the table, so that there's always going to be room, but I'll address what happens if you need more space in a bit, either today or next week. So I'm going to imagine I have some positions in here. So just think of it as an array. It's just an array. I'm just going to call this a hash table. And imagine I have a bunch of records I would like to put into this hash table. So let's see. Can you please give an example of hashing? We're going to talk a lot about hashing the next couple of lectures. So don't worry, we're going to be going to all the fundamentals of what hashing is. So I'm going to show you the big idea of hashing here right now. So imagine I have a whole bunch of records. So imagine I have a bunch of records I would like to put into this so-called hash table. So I say I have 3 records here. Maybe I have up to n of them. So I have n records I would like to put in. So what I would like to do is have my get, my put, and my remove operations. I would like to be able to have this in a way, like I mentioned, where I know exactly which slot in this table I'll find that record. So the whole idea here is that if I can put it into a spot where I can easily compute where its location is, I can try to achieve constant time. So watch this. So I'm going to construct something called a hash function, which I'm going to define what that is in very careful terms in a little bit. And what the purpose of the hash function is that it takes the key of my record, we feed it over to this hash function, and it tells me a location to put my record for the insertion, or if I ever want to look it up, it will tell me where it should be. So for example, suppose that in this case, it puts it into position number 2. It'll put, say, it right here. Likewise, I could do this with the other ones. Say if I put the second record in, maybe it puts it down here at the bottom. And say the third one, maybe it goes just above K1. So I have K3, V3, and any entries I don't use, I'm just going to presume them to be null for the sake of our discussion. Maybe Kn goes right here. Kn, Vn. So the point is that this hash function tells me a location where I could put that record in this table, which remember, the table is just an array, but you can think of it in a lot of other ways, which as we're going to see. So the idea here is if I can compute this location to put it in the table in big O of 1, so in constant time, under very specific circumstances, if I were to use, for example, get, put, and remove, our goal here is I want it so that if I were to use get, put, or remove, which each will use this key to be fed into this hash function, I want all of these to take big O of 1 in the average case. So it's going to be big O of 1 average running time. So that's going to be what we're going to be aiming for. Is I would like to have this so that get, put, and remove all take constant time on average. Now, I cannot guarantee this in the context of the methods I'm going to show you here, but every bit of what I'm going to tell you is easily something that does actually exist. It's just that in practice, I'll show you some ways to achieve this in a rather efficient way. But most certainly, that'll be one of the main assumptions, was that the assumptions that I'm going to give you allow you to obtain that average running time of constant time, which is much faster than the ones we have over here. Because remember, all of those, you're going to have to examine all of the elements, right? But here's the thing. Remember, I haven't told you anything about this hash function. Because remember, it takes in a key, and it tells me a location where to put the records. So you might say, Dan, what exactly does this thing do? Like, how does it know how to do that? Like, that seems rather, I don't know, it seems kind of magical, right? Like, how does it know, like, omniscience-wise, like, how does it know, like, how to do this? Because remember, if it could perfectly place all of these entries in here without me having any issues, the key thing is the any issues part. You can see how quickly I could quickly access all of them, right? I would use the key, compute the hash function which takes constant time, and I could get it immediately, right? But we're going to see that's a little bit more complicated than just that. So I thought before we get into one major issue here, I thought I would give you an example of how you might use one of these hash tables. So you can imagine having a hash table. And now remember, the big thing we're doing is we're using memory to reorganize the data so that I can speed up the lookup times. And the whole idea is that I'm going to try to make it so that I don't have to examine as many records if I have a unique way of finding out where it is. That's the most important part. So just to give you an important aspect of this, in the hash table, the hash function h must give a position for each ID or key. Must give a position for every ID, as I kind of alluded to over there. So I thought it would give you an application for how you might use something like this. And remember, one thing that you will see is that you have control over the size of this table. So the capital M, you have control over this. So in practice, you would select this in a way that would make it so that you could fit all the data that you need, or enough of the data such that if you need to make it bigger, you can always resize it. And you remember, it's just an array, right? We know how to resize an array. More on that probably next lecture. So just as an example, consider all possible student IDs at the University of Regina. So each has digits as follows. So each has digits, and we have 9 digits, I believe, in our student numbers. I'm going to call it D8, D7, D6, all the way down to D1, D0. So you can imagine I have this representation of each student number. So, a question for you. How many possible student numbers could it possibly exist? So, how many are possible? So if I were to find out, okay, how many are possible for all possible combinations of these student numbers? So I want to know how many of these are possible. So remember, student numbers, it can have a 0 in it, it can have a 1 in it, it can have a 2 in it, it can have a 3 in it, all the way up to 9. And remember, the digits themselves are technically independent of each other. So just keep in mind that they're independent of each other. So I'm not thinking of factorial. That's a good first guess. I'm not thinking of factorial. So I want you to think about it instead like this. So in each digit, I have 0, 1, a 2, 3, all the way up to a 9. But this is true for every one of the digits. So if I want to think about how many are possible, I have 10 possibilities, and I have 1, 2, 3, all the way up to 9 spots, right? So you can think of it as 9 blanks, where I could put in up to 10 different options. So I have a very close answer in the chat. So far, somebody's saying 9 to the 9. It is very close. It is 10 to the 9, 10 to the 9, 10 to the 9. Very good. This is just because each digit has 10 possible values. They're independent of each other. So the total possible number of these is 10 to the power of 9. That's rather big, right? Which I must stress is much bigger than the table itself that I'm going to present to you. So this table that I'm going to show you, I'm going to have 0. It's going to have some more. Suppose that it has 10,001 slots in it. Suppose this is my table here, and it has 10,001 slots in it. You know right away that not all of these are going to fit in here, right? So I've delicately picked this number. It's really not special or anything. It's just the point is it's much less than this. So I have a question for you. Are all possible student numbers going to fit in here? If you assume that each one of the spots is supposed to have 1 record in it. No, right? This is a lot more. Now, but keep in mind that in practice, you may not necessarily need this many slots, right? So if ever you need to make more space, you can always resize the table and use the so-called hash function to recompute every one of the spots. That's very expensive to do, but I'll talk more about that later. The point is that you most certainly cannot fit them all in. That means that there's going to be circumstances that are going to look like this. So remember how I had my picture over there where I had like my different records? So suppose I have 2 IDs, I say 2 student IDs. So I have ID 1 and ID 2. I have 2 student IDs. Suppose I first inserted the record associated with ID number 1 using this hash function. Remember, I haven't told you what the hash function does, other than it gives you a position in this table. And suppose it puts it right here. So ID 1 goes in here. What happens if I give you suppose that this exists. Suppose that there's another ID, and keep in mind there's many more IDs than there are spots in this table. So this is a very likely thing you're going to run into. Is that I suppose I have another ID that when I use this hash function, it gives me the same exact position. So the question is, what do we do? And now that is the ultimate question that we're going to run into, is what do we do when we run into this? Because I want to put ID2 into this table, but my hash function would put it in the same exact spot in this scenario. This is what we call a collision. So this is what we call a collision. So I'm going to say these two, and the phrase that often is used when we talk about what the output of the hash function is, we call it hash. These two hash to the same position. To the same position. This is what we call a collision. And these collisions are a very big problem for us when we're doing hashing. At least it's one of the big obstacles you run into when you're first thinking about hashing. It's what we call a collision. Whoop, a collision. For some reason I wrote S there. A collision. A collision. So what we need to do is find a way to resolve these collisions. That seems to be one of the biggest things we need to deal with. So there's a lot of things we're going to have to keep in mind when we design a hash table. For example, what's the size of the table? Actually, let's recap all of these things over here. I want to tell you about some design considerations for this. So remember, I haven't told you what a hash function exactly does other than it gives you a position. So right now, I am holding on to you right now and I'm saying, don't worry, be patient. I will show you what a hash function exactly is shortly. It'll be right what I'm going to talk about next here. So it's coming very, very soon. So remember, right now we're just trying to use some memory to try to spread out the records so that I don't have them all constrained into one spot so that I have to traverse through all of them. The whole idea is I would like to have it so it's just like, because remember, in an array, I can access those positions instantaneously, right? It's a nice thing that I have. I can do it in constant time. So I would like to take advantage of that fact. So if I can spread out these records in this table, and I know exactly where they are, that should be a massive, massive performance boost compared to the linked list. So I want to talk about some key things, key design issues. And I've mentioned about all of these, I think. So key design issues. So determining the size of the table is one. I'm going to give you some advice on how to determine the size of the table. Determining the ideal size for the table. So depending on your application, the size will differ. But if you, for example, know exactly how many records are going in this table, you could figure this out, right? But there might be a very specific value you might want to make depending on what we're going to do with these collisions over here. So the next big thing is, of course, the selection of the hash function. So how you determine the selection of this hash function, the hash function. So it should be efficient to compute. So this is one thing I would like to have. Now, it isn't true that all hash functions have to take constant time. It has to be, we would like it to be efficient. Ideally, a big O of 1, worst case. Worst case time. I would like it to take constant time. That's the one thing. We want it to be very fast to compute it. I want to know where that location is in the table very quickly. It causes few collisions. And this is going to be the assumption I was alluding to. I would like to have this hash function have the ability so that it could spread the keys uniformly across this table. Just like if I took a butter knife and I spread it across a really long piece of bread. So I just want to make sure it's nice uniformly spread across. So I would want to make sure that the hash functions, if it cannot theoretically do it, it does it quite close to this, depending on what we're dealing with for the keys. So you're going to find that the choices I'm going to give you here will do the latter, but there are ways to actually achieve this in the most purest sense. It must spread keys uniformly across the entire table. You might say, Dan, why does it have to be across the entire table? Well, if I'm using that memory, using all of that space in that array, I don't want to waste it, right? Across the entire table. So we will make this uniformity assumption. Uniformity assumption in our analysis or analyses. So I must stress that whenever I talk about the average case or what you should expect to happen, I'm always doing it underneath this assumption. So I need this assumption for the expectation I had at the beginning where I talked about having big O of 1 average running time. This assumption is critical for this, for all of the techniques I'm going to show you. The last and third one is the collision resolution. So what do we do when we have a collision? So we're going to talk about collision resolution. So this is what we're going to primarily focus on, is collision resolution. How to deal with collisions. So if we can deal with these collisions, and we can have all of these bits and pieces, we're in a good place to be with our hash table. So before I proceed with what a hash function is, are there any questions? I'm happy to answer any questions. So just remember the big picture here is I want to have this hash table. It's going to be able to have it where I could do my dictionary operations. And it's going to be where this hash function is going to have the ability to take in the key and it'll tell me a position in the table and I'll put it right there, or that'll be telling me where to look for it. But the issue we have at hand is that it could be the case, just like when we had just our typical example, because you can imagine this just being like a table of length with only one slot in it. And you can see very quickly that this actually degenerates back to our discussion about the linked lists, except we don't know what to do with all the rest of those entries when we run into a collision, right? But the whole idea is we would like to take advantage of the fact we're using memory to store and try to uniformly spread the records. So are we assuming that the table is sorted? Nope. No assumptions about the table being sorted. Yeah, so you're going to see very quickly that these keys are going to sometimes be very erratically placed around in the table. But that's a good question. That's a very good question. So you're going to see that I'm not going to be doing something like a sorted array. We're going to do something very different. So that's a wonderful question. Very wonderful. That's actually a really good question. Because we've seen, for example, with the sorted array, we got some perks from that. The whole idea here is that this hash function should be very cheap for me to compute. It'll tell me where to go look. That's a good question. So let's talk about what a hash function is. So depending on how far along we get today, this might be the main thing we'll focus on. So remember, the main intuition here is that I don't want to have it so that I put all of the records in one spot. So you know how when I have a linked list, right? Whenever I do my put operation, say in an unsorted linked list, right? Like if I have an unsorted list, I put if I have my friends and I'm doing them as insertions in my records, I just put them all in one bin, right? So if ever I want to go looking for my friends, I have to look through this entire collection, right? So I have my friends here. They're all sort of just hanging on out. But if I ever need to insert another friend, I need to make sure I examine all my friends, make sure they don't have the same key as me. So, like if I put Pusheen here, I need to make sure that Pusheen isn't actually already in here. So the intuition is that I'm going to have, and imagine these slots like buckets. And the whole idea is that on expectation, so what I should expect on average is that if I have this uniformity assumption, that all my friends will go, at least on average, will go one into their own buckets. Now, this will not be how it exactly plays out all the time, but this is just what you should expect. Is that on average, each will get their own bucket, just like each will get their own slot. So that's why I'm telling you that you're going to expect that we're going to try to make it so that we can try to get them so they're cleanly spread out like this, not all stacked together and clumped in one bucket. And these buckets are our slots. So hopefully that gives you some intuition for what we're going to be doing here with our hash function. So let me define what a hash function is. So the first thing you need to know is that keys in a dictionary can be any type. That's the first thing you need to know. So I'm not making any assumptions about the keys being to be smaller or bigger. They don't have to be comparable. They could be things like an integer, which indeed those are comparable. It could be a string. Those are comparable. A character, I can compare those. It could even be an array, for example. It could be other types. I can even make the keys data structures, which is kind of wild. So keep in mind that I'm not making any assumptions about what the key is for terms of type. The key thing is that I have some way to represent it. So I'll focus primarily on when the key is a string, because that's very often what you'll run into. So a hash function. So I'm going to first give you the definition of a hash function. So h of key, so it takes the key in as input, and as output, it has two parts it computes. There's these two functions called f and g, where it first applies g of key, and then the result of that is applied to f of whatever that is. So I do f of this thing. Hash function has two parts. So I'm going to define what f and g are. A hash function has two parts. Two parts. The first one is called its hash code. First is the hash code. It's a function. G, give an input key that produces an integer. Because I would like to spread the records across the entire table, I would like this number that it spits out to me to be able to be large. I would like it to have the ability to become large. Ideally, we want the integer to be large. So, because remember, the size of the table might be in the thousands. Like I'm talking like you can make these tables quite big. Like you make it like 10,000 entries if you want. So we need to make sure that the number we're going to get out of this is going to be rather big so that we can try to get it so that whatever position I give you, it'll try to be somewhere further down in the table as opposed to all clustered up near the top. To be large, to use the whole table. So that's what the hash code is. It's just this function G. The second part is the compression map. This is probably the easiest part of this. So the compression map is a function So I'm going to use that mapping notation I used at the beginning of the lecture. A function f is going to take as input an integer. So it takes an integer as input, and it produces as output a number between 0 and capital M minus 1. So this is just a position in the table. So that's what a hash function is. It's just these two parts put together. So first, it applies the hash code to the key. It gives you an integer. The compression map will take that number and map it into a position from between 0 and m minus 1. So that's what these two parts are. Are there any questions about this definition? So we'll play around with designing hash codes next, but I just want to make sure you understand this definition before we go. Oh, before we proceed. So remember, this one's job is just to spit out an integer. This one's job is just to tell me a position in the table. Because remember, this is the thing that's going to take whatever that number is, and it's going to try to kind of map it onto a given spot in the table. So if we get a really big number, it will perform, say, for example, a wraparound to put into the appropriate spot. You'll find very often that the compression map just uses the modulo operator, or mod. So whatever the output of this will be, it's usually that mod the size of the table, for example. Usually the compression map is a much simpler part of the hash function. Okay, are we okay with this definition? Give me a thumbs up if this is going okay so far. So that's the formal definition of a hash function. So just remember, the game in town is we come up with this hash code, and then all we have to do is we just try to make it so it fits within the confines of our table. So let's talk about designing hash codes. So there's a lot I can talk about with hash codes. I'm going to reserve this primarily to thinking about how we can design a hash code that in practice, especially on English words, like if I give you a dictionary full of a large amount of English words, for example, it will behave similarly to our uniformity assumption. So something that will cause very, very few collisions. So a good hash function. It's not, so it's practically speaking, will kind of be like our assumption. But remember, this is an assumption I'm making that the hash function's good enough to do this. So just keep that in mind. And there's a lot of different ways you can achieve it, but some of those are beyond the scope of this course. Hashing is this very matured subject in computer science that has all sorts of fun things about it. So, let's talk about hash codes. So I thought what we could do today is we'll talk about, that H is looking a little sad. I'm going to fix that. So what I'm going to do is we're going to consider taking a string and converting it into an integer so that I can use it for computing this hash function. So we're going to come and derive a hash code that's going to take a string and it's going to spit out an integer. I think that's a pretty good place for us to start. Let us consider converting a string to an integer. So we'll start with something kind of basic here. So can somebody tell me, if I wanted to look at an individual character in C++, how can I convert that into an integer? You can either just say it, what the term is. You could tell me what code you would use for doing this. There's a lot of different ways you can do this. But I'll definitely show you. I will show you. So if I give you one character, what can I use to convert that into an integer? Any ideas at all? Don't be shy. Yeah, well, exactly. Somebody brought up ASCII. Yeah, no, the beautiful part about characters is that they always have a corresponding integer associated with them. So you can use casting, you can cast the character to an integer. Exactly. So the idea is that you can convert, like if I give you one position in the string, so given a position I in the string, we can use casting, right? We can cast that character to an integer. So you can do this as follows. So the first step would be that you make a character. Okay, I have a character C. I'm going to be, say if I call the string, we'll call the string S. Call the string S. S dot at, we can use the at. I know there's other ways we can write this out as well. I can go S dot at, and that could give me the character at position I in the string. This is at least one way to do it. Next, the next step, we could just simply take an integer. We declare an integer. I'll call it value, and we're going to assign it to just be, I'm going to cast C to be an integer. So you might recall how to cast to different primitive types. That's all I'm doing here. So you can see how you can easily take the idea that I just gave you here, and all you do is you just go through a loop, right? You can just go through a loop and go through each one of the positions. You can convert any one of them, any one of these positions, a character there, you can convert that to an integer. So just keep that in the back of your mind when we talk about how we can come up with a hash code. So then we can apply some function. When I take these and convert them into integers, let's try to use that to make a hash code. So let's make a first attempt at this. So I think we'll start with a first attempt. And remember, our goals are try to avoid making many collisions happen. Another thing, of course, is we want this to be fast and easy to compute. And if for practical reasons, you can always presume that the length of the string for our discussions is of a constant length. So if I give you a string, it'll always have a fixed length. So if I give you like student numbers, they had 9 digits, right? So I would always presume that student numbers have 9 digits. So I think this might be the first place for us to start. Let's start by doing this. So I'm going to start by making a hash code that takes in characters like this. So I'm going to just write it so it's kind of backwards. So I'm going to have CK minus 1, CK minus 2, down to C1, C0. So this is going to be the way I'm going to write out all the characters. So these are just notation for each one of the symbols. So this is each one of the characters in my string. So imagine this is the string I give as input. Here's an idea for how we can compute an integer. So I'm just going to go through all of these characters. And I'm going to take each one of the characters, cast them to be an integer, and I'm just going to add them up. So this is my first attempt. This is the first attempt for determining a hash code. I have a question for you. What do you think of this hash code? So keep in mind the design aspects that we talked about. Is this a very good hash code? So if I could give you a hint, remember that these are strings, and the techniques I'm going to show you are best applicable to, say, if I give you a giant list of English words. So you just got to keep in mind, remember, we want very few collisions to happen. In fact, we would like, in theoretic reasons, we would not like any. So while you're thinking about it, I'm going to give you one reason why this might not be the best of choices for a hash code. This is not a great hash code because, well, at least these are a couple of reasons. I know that somebody out there might think of the other reason. The first one that I'm thinking of is that it doesn't really produce large integers. It produces relatively small integers. Remember, all I'm doing is adding up what their values are. If I have a hash table that has, say, I don't know, 10,000 slots in it. If I only have strings of length 5, and you think of the ASCII values or the ASCII codes, you're not going to be getting up to those really large values, right? That's one problem. Think about collisions. What's another problem with this? Remember, all I'm doing is I'm adding the values of the characters. So think about it. Think about it. Is it that, so for example, when I put a letter, if I have a string like AAA, each of those A's has the same value, right? Ah, yeah, perfect. Some people are there we go, we got it. Some people have some really great ideas here. Is that, yeah, they might have the same value even though they're not the same string. Exactly. So some words actually may have the same value. In fact, it's even worse than that. Now keep in mind that this indeed is prone to the fact that there might be some way you can add the character values such that it equals some total that is the same position. Sure, we're not going to be able to do much with that. It's sort of just a circumstantial thing, at least at this stage. But the biggest problem is that some words may have the same value, but it's even worse than that. So it ignores the ordering of the characters. That's a big problem, right? So that's even worse. That's even worse. So for example, if I gave this stop, pots, tops, and spot, and you'd agree with me that stop and spot are two different words, right? Likewise, pots, tops, these are all different words. They do not have similar meanings either. These are all very circumstantial words, but they're just, this hash code does not take that into consideration. That's a big problem, right? So that means that any permutation of characters, as long as they're the same set of characters, they will output the same integer. So if we take it to the example of our student numbers, you would agree with me that there's going to probably be a lot of student numbers that use the same numbers of zeros, ones, and possibly twos, or threes, or fives. You can probably find that there's a lot of different combinations of them that will have the same numbers of zeros, or ones, and twos, and threes, and fours, and fives, possibly. But the point is that the ordering isn't taken into account. That's a problem, a big problem. So this, I would argue, is not a very good hash code. So are there any questions about this one and how this works just before we proceed? So I would not recommend using this in practice. Nor does it actually even meet the basic criteria of what we would like. So the biggest thing we're going to do next is I would like to eliminate the second reason, and I would like to make sure that the numbers are much bigger. So I want to resolve these two issues. By no means do I claim that this is perfect. There are other kinds of hashing schemes that are actually what we call perfect hashing. They're beyond the scope of this course, but they do exist that do allow you to have it where you can actually have where there are no collisions. But there's a lot more setup to them, and there's a lot more of that mayonnaise and mustard, the sweet, sweet mayo and mustard. So I'm going to show you a relatively fast way. Actually, it's a fast way, assuming that the length of the strings are constant, to improve upon this. So I could actually give you one that is actually a fairly effective in practice method of computing the hash code. So here's a much better design. So here's a second better attempt. So I want to resolve those two issues over there. So here's the thing we're going to try doing. We're going to be developing something called a polynomial hash code. So at first that sounds really daunting, and what I'm going to write down is going to look a little daunting at first. But I assure you, the pseudocode and the algorithm is really simple. So we're going to use something called a polynomial hash code. The reason why we had this issue before is I just added up each one of the character's values. What I do is suppose I take the position into consideration, what I would like to do is I would like to take each one of those character values, multiply it by some constant I select, raised to some power. And because each of the positions are going to be some power, but I'm going to do it in the form of a polynomial, starting with the highest degree, then each successively the exponent's going to go down by 1. And the hope is that this is going to add enough kind of what we would call salt and pepper. We're going to try salt and peppering this a little bit more so that it will try to take into account the ordering, because now I'm actually doing something different for the two different positions now, as opposed to just being neglectful or ignoring it. So I'm going to let the string, S be written in the way that I wrote it over there. So just be very mindful of the indices here. So just be very mindful of the fact that this is I'm using the highest index at the furthest left position. So just keep this in mind. So you can convert each of these into an integer, right? So convert each character to an int or whatever type. Say if you need more bits, use more bits if you need it. As coefficients of a polynomial. So here, I'm going to show you what this is going to look like. So I warn you, it's going to look a little daunting at first, but I assure you, when you actually see the algorithm, you're like, Dan, that's so easy to do. Why did you show us this? It's because you need to see where it comes from. So what I'm going to do is I have this polynomial I'm going to write as follows. So I'm going to put the casting in. So I'm going to convert this character to an int, and I'm going to multiply it by some value called x, raised to the power of k minus 1, plus I'm going to cast ck minus 2, multiplied by x to the k minus 2, all the way down to casting c1 to an integer times x to the power of 1, plus casting the last character. Now, I haven't told you what x is yet. I'm going to give you a source for reliable values for using for x on an English dictionary. So if you're wondering where I'm going to get this from, there is actually you know how there's the optional text in the course outline? They actually provide some of these values in there, and they describe the experiment that was done. So in Goodrich et al. So if you're looking for more details about this, you'll find this actually in the optional or supplemental text that's in the course outline. So according to these folks, some good choices are 33, 37, 39, 41 for x. So what they did in their experiment is they experimentally determined these. These were not calculated out in some formal analysis. They were done through experiment. So these were determined using a 50,000 English word dictionary. And it was done, I believe, with two variants of lists in Unix, I think. Unix So they did this over a Unix system where they did the comparisons. So they found these values worked extremely well in practice. In fact, they produced no more than 7 collisions in their experiment. Which, that is really small in the perspective of that number, right? Like, that's a lot of words. So you only run into, they produce fewer than 7. Now, for those that are curious, there are other options out there. So, for example, if ever I asked you on an assignment to, say, compute a hash code, any one of these values for X I'm going to give you here are perfectly fine to use. In fact, I encourage you to play around with them. So another example of a good hash code is, for example, the Java programming language actually has their own for strings. If you ever go string.hashcode in that language, it uses 31. So if you can compute this polynomial, you just use one of these values for X, and you can indeed compute this. And it's very natural to do this with a loop. However, there's a couple of technical problems. So, how many of you here have heard of something called integer overflow? Has anybody heard of the term or the phrase integer overflow before? Don't be shy. Give me a thumbs up if you've ever heard of that before. Ah, yes. So remember that if I give you an integer, it is still a finite representation using some fixed number of bits, right? So if I try to compute a value, and remember, we want to compute some rather large values here. If the numbers that I'm operating on get too big in the middle of this calculation, we can run into an issue called integer overflow. So we don't want them to get too big in the middle of the calculations. Otherwise we'll get inaccurate results. Like, as in, like, we will not actually compute what we're expecting. The integers get too big. If you're wondering what I'm talking about, remember, the number of bits used to represent an integer is fixed. So if you try to add 1 to the maximum possible value for an integer, or 2, or 10, or 20, it can cause very, like, if you're looking for a positive integer and you start adding to the largest possible int value you might have, you're going to be very surprised. You might run into a negative value, or you might end up in some erratic value that you're not sure about, unless you're familiar with the notion of signed types. If, say, if you're using the ability to have, say, an integer that can be negative or positive, some of them use what we call a sign bit. So if you make it a little too big, it overflows by carrying into the additional bits that cause it to flip the sign, depending on what kind of integer you're using. Regardless, you're using, we can use other kinds of integers as well to make for more bits. This is why I mentioned that you might need to, if you need to use more bits, use more bits. Like, you can use long, for example. The chat is mentioning a wonderful suggestion. You can use things like long as well. These are things that do exist to try to hammer this, get this as less of an issue. But do keep in mind, remember, these numbers might still get really big. I would like to keep it so that it's still going to be a value that's between the range for my table. That's what I would like at the end of the day, regardless. So as long as I can do that, we're okay. Now, here's the beautiful part about this, is that there is actually a way to rewrite this polynomial in a way that you group the terms, but reduce the number of multiplications. For the purposes of time, I'm not going to go into many details about how you group the operations, but you'll notice that when I do this, I have C1 times x to the k minus 1. Now notice that regardless, if I were to multiply x by, say, x again, the exponent goes up by 1, right? So what I can always do is I can imagine I start off with computing ck minus 1 times x plus ck minus 2. Then I multiply that by x. That would cause the exponent to go up by 1, right? If I do this again with the next successive term, if I multiply that by x, the exponent will go up by 1, but it'll do that everywhere, right? Because I could distribute this product. So this is actually at the heart of something called Horner's method. So to compute the hash code, we will use a variant of Horner's method, which must I stress that this actually does half the number of multiplications. So it does about half the number of multiplications than if you did compute this naively using a loop. So it's about half the number of multiplications than the naive approach of just calculating this out straight out. That's one advantage it has. The other thing is, because of the way it composes the terms, it also falls right perfectly into the hands of modular arithmetic. So that's what the variant in this is going to be. So I'm going to apply mod to keep the numbers from getting too big. And let me write out the algorithm here for computing this hash code using the polynomial hash code. And this will be a perfect place for us to stop when we get here. Because I will tell you, the algorithm's very short. And you'll look at this and be like, Dan, why didn't you just show us this? Well, I have to show you everything else first to really kind of convince you that this is a good idea. Or at least I think it's a good idea. Okay, so let's proceed. Let me write out the algorithm here. So if you're curious about Horner's method, it's used quite a bit actually in scientific computing. So if you're interested in that kind of stuff, Horner's method actually is used quite often in there for evaluating polynomials. That's actually how we're using it here. Algorithm, I'll call it hash function. So I'm going to give you the string the string s and that x value. You'll find very often in practice that you might actually just hard code in this constant or make it a constant variable that you can change in your code. Here I'm just going to make it a parameter. So just remember the way I'm indexing the string here. The same way I've been doing it up to this point. So notice it's backwards. And a value x. And the output is it's going to give me a position. So I'm going to put together the hash code with the compression map. So you're going to notice I'm not actually going to present you the compression map. It's going to be implicitly written in this algorithm. Because I'm going to use that fact, the compression map is going to be implicitly written out in this. In fact, I'll write it actually explicitly at the end, but we'll see. So position for S in a hash table of size capital M. So here we go. I'm going to start off by putting an initial value for val. I'm going to cast ck minus 1, which is the first character, right? Then for I is assigned k minus 2, I'm going to go down. So I'm going to decrement instead of increment. So this is often how you can write down if you ever need to go down as opposed to up with your for loop. You can write down to 0. You could do the following like this. And watch this. Val is going to be assigned val times x plus, I'm going to cast ci And I'm going to apply mod to this. So remember, in C++, the mod is the percentage operator here. And of course, I'm just going to return, at the end of this, I'm just going to return val mod m. So that's actually the compression map explicitly written out. So this will actually guarantee that the numbers aren't going to get any bigger than the table size. So we don't have to worry about integer overflow anymore, only within the context of only this operation at that one stage. So this will help prevent it from getting too big. So looking at this, one quick thing you'll notice is if k is if k is constant, this takes big O of 1 time. It takes constant time. It's actually, the time complexity is big O of k. So I'll encourage you to try that out. So when we come back next time, we're going to talking about how we can resolve collisions. So we'll talk about collision resolution policies. So when we come back on Monday, we'll talk about that. I want to say thank you very much and have yourself a beautiful day. I'll see you later.